I'm here to talk to you about hydrogen, and in particular, the importance hydrogen has to both our present and the future of society, the world. It's a very important topic. So to start, I'm just going to talk a bit about hydrogen itself, just to check we're all on the same page. So hydrogen, when I talk about H2, is the lightest diatomic molecule there is. So it's only got two hydrogen atoms bonded together. And hydrogen as an atom is quite interesting because it's the most abundant element in the Earth. In the universe. And if you look at the universe at large, 91% of all atoms are hydrogen atoms, 9% are helium, and a very small quantity are other elements. So there's absolutely loads of it in the universe because it's so simple. It's just one proton and one electron bound together. But on Earth, most of your hydrogen is found in water molecules. The Earth is a very large proportion of it is covered in water, so that's where we find a lot of our hydrogen. And you also find it in anything with carbon in it, so anything living, there's lots of hydrogen in. So you find it everywhere, apart from rocks, really. Everywhere else you'll find hydrogen. So then the question is, if we have hydrogen gas, what can we use it for? So this is I'm going to give you a few minutes to sort of think, is there any way you've heard of hydrogen being used or might be used in the future? And if you have any ideas, just type them in the chat and then we'll see who's guessed correctly. So yeah, think of some ideas and type away. So I see we've got a suggestion of hydrogen buses. Fusion reactors. Yeah, that's a very cutting edge one. Energy generation. That's a good idea. Rocket fuel. These are all very good ideas. Yeah, you're on the ball today. Lots of good suggestions. Nice. Yeah, so I think you've got some good suggestions there. So to cover some of them, one which I haven't seen is that hydrogen is sometimes proposed as a replacement for central heating systems, because currently central heating systems are based on natural gas, so they burn things like methane, which is obviously a CO2 emitting process. So some people think you can replace it or partially replace it with hydrogen. You do have problems of then having pipes full of flammable explosive hydrogen. So there's pros and cons, but that's something we might want to use it for. As mentioned, hydrogen vehicles are a popular thing to talk about. So you have hydrogen cars. There have been hydrogen cars made before. They're not a new thing, but they've never really commercially taken off. Possibly because the idea of a hydrogen petrol station is a scary and explosive thought. And as someone pointed out in the chat, hydrogen buses, however, are in use. So there are hydrogen buses in use in London, where you can refuel them at a bus depot. So you don't have as many storage concerns. And also, I was interested to find out that during the London 2012 Olympics, they had hydrogen-powered taxis to show the commitment of London to net zero. They didn't last very long after the Olympics, but they were there as a trial technology. And moving to other forms of vehicles, hydrogen is floated as a fuel for planes. So whether you use a fuel cell or you burn it, it's one thing being proposed as a net zero carbon neutral fuel for planes. and it was used a very long time ago for a different form of air travel. So in 1937, a blimp crossed the Atlantic and then tried to land. It was filled with hydrogen, and it unfortunately set fire and exploded. So this is the Hindenburg disaster, and 36 people died, unfortunately. Um, and this was the earliest example of someone using hydrogen to travel. Though the blimp is meant to be filled with helium, which is a noble gas, so it's inert, and wouldn't have exploded. But because they didn't have enough helium, they filled it with hydrogen, and some very bad consequences came from that decision. And as someone said in the chat, it's used as rocket fuel. Because if you burn hydrogen and oxygen gas together, it's very exothermic, only produces water. And if you propel that downwards, you can shoot your rocket all the way up. And that's what they use to go to space. And some of the other things in the chat mentioned were fusion reactors. So fusion reactors use different isotopes of hydrogen. So they'll use a deuterium, so that's hydrogen with a neutron in it, and tritium, which is hydrogen and 2 neutrons, and basically fuse them together in a radioactive process, and generate a lot of electricity. Hopefully that will come online within our lifetimes, because that would solve a lot of energy problems, but there's no guarantee. But none of these are what hydrogen is used for today in by far the largest quantity. And to understand this, we're going to have to look at what hydrogen is used for today. So last year, in 2024, 97 megatons of hydrogen were produced. Now, a megaton, to put some context on it, is 1 million tons or 1 billion kilograms. And 1 billion kilograms is the equivalent of 6,700 blue whales, if you have a concept of how heavy a blue whale is, or 670,000 cars of weight. So 97 megatons is about 67 million cars worth of weight. That's how much hydrogen was produced last year. So we were talking very large quantities of chemicals. And almost all of this was used in either oil refining, where they take the products from oil, which are sort of a mixture of very long chain hydrocarbons, which aren't very useful, and they crack them into smaller ones, or they hydrogenate alkenes into alkanes. So basically, they take products from oil and make them into more useful ones. And the rest of it, about 60% of it, goes into other industrial uses. And these industrial uses are mainly the production of ammonia. So 60% of the industry use, or 32 megatons, goes into making ammonia, which is very important because ammonia is then used to make fertilizer. So about 70% of that ammonia production goes into making fertilizer. The rest of it makes methanol, which is a very important chemical as well in its own right, and the other 10% goes into making steel, which again is a very important material. So you can see that hydrogen is very important to industry, to materials, to processing, and also to farming and agriculture. So focusing on the farming side, you need to think about how hydrogen is used to make the ammonia. So as you may have seen in GCSE chemistry, we use a process called the Haber-Bosch process. So this was invented all the way back in 1913 as a way to take nitrogen out of the atmosphere and make ammonia, which is a process previously that could only be done by bacteria in the soil. So it's sort of a way of cheating the nitrogen cycle, which we'd never been able to do before as humans. Now this process, say you take nitrogen from the air, so that's very abundant, 80% of the air is nitrogen, it's not very difficult to separate. And you mix it with hydrogen gas. You compress them and you heat them up to around 400 degrees, and you put them under a lot of pressure, so 200 atmospheres of pressure, so a large amount of pressure with a catalyst, and they make ammonia. And ammonia becomes a liquid at around 6 atmospheres, So that condenses and can be collected, and then they recycle any unreacted nitrogen and hydrogen, and that's how you can produce ammonia. And this process is absolutely enormous on a global scale. So it's estimated that the fertilizer you produce from this ammonia is responsible for feeding half of the world's population, which if you think about it, this process is responsible for the food for 3 to 4 billion people. So it's probably one of the biggest contenders for the most revolutionary technology of the 20th century. That or lithium-ion batteries. But this has a pretty good argument. And because it's so large and underpins the entirety of agriculture across the globe, it's responsible for 2% of global energy consumption. 2% of all the energy used in the entire world is just this process, which is enormous. So if you're thinking about how do we reach net zero on a global scale, then this process is an enormous contribution, absolutely enormous. So then we have to think, how can we make this process net zero? Where are the carbon intensive energy inputs coming from? And one is literally the input energy. So you need energy to heat the reaction, you need energy to compress it to 200 atmospheres, and all that comes from some sort of energy generation or electricity. So that's not too bad, because if we can produce our electricity in a renewable way, so either with coupled renewable energy, hydroelectric, wind, solar, whatever, or nuclear power for a low carbon intensity generation, that's fine. But then you have the question of the input chemicals. Nitrogen is fine because you can get it from air, and you can separate nitrogen from air using electricity, so that can be green. But hydrogen's where it becomes tricky, because hydrogen is produced in a different way, because we can't just pluck it out of the air. And unfortunately, hydrogen is produced from fossil fuels. So 85% of all the hydrogen we made last year came from fossil fuels. The other 15% came from byproducts of other processes. Only less than 1% of hydrogen was generated in a low emission way. So that's either capturing the CO2 emissions with carbon capture storage, or from electrolysis, which I'll come on to later. And the reaction used to make the hydrogen is here on the top right of the slide. So you take a molecule of methane and you react it with a molecule of water at a very high temperature. And the hydrogen atoms are basically stripped away from the carbon in the methane and the oxygen in the water, and they can form 3 molecules of hydrogen. But then the leftover oxygen and the carbon come together to make carbon monoxide. And then there's a second reaction called the water gas shift reaction, where carbon monoxide reacts with another molecule of steam, where again, the hydrogen atoms are stripped away to give you a hydrogen molecule, but your leftover oxygen reacts with your carbon monoxide to form carbon dioxide. So overall, we take 1 molecule of methane, react it with 2 molecules of water, and get 4 molecules of hydrogen, which is great. We're producing loads of hydrogen, but we get a molecule of CO2. So it's a directly CO2 emitting process. Even if all the electricity in the world was green, produced solar or wind, for instance, this process would still be emitting CO2. And that's obviously a problem if we want to reach net zero, because this is a huge process. But we can't stop doing it because of the industrial importance, because we still need to produce the fertilizer to feed people. And we still need to make steel, and we still need to make methanol, and we still at the minute need to refine oil to make plastics. So there's a big problem in how we can make this industry net zero. And it's made even more difficult because hydrogen demand is only forecast to grow. So we'll need more fertilizer going forward, but also hydrogen for other uses. So all the uses we talked about earlier, so our hydrogen cars, our hydrogen fuel, if we use hydrogen heating for rockets, Fusion reactors is slightly different. And if we use hydrogen as an energy storage medium, which again I'll come on to later, all these things require even more hydrogen to be generated, which makes our decarbonisation challenge even bigger. And unfortunately, this specific decarbonisation challenge is often overlooked because it's not just decarbonising electricity. It's an industrial process that's very, very difficult, and it will probably be one of the last things to be decarbonised. And the way we could decarbonize it is basically by producing our hydrogen in a different way. So electrolysis is one of these methods. So here you produce hydrogen oxygen gas directly from water using electricity. So it's no longer a directly CO2 emitting process because there's no CO2 made. There's no carbon involved anywhere. So the only way you have CO2 emissions is from the input electricity. So if you can decarbonize your electricity grid, then you can decarbonize this process. It doesn't require a very high voltage, only about 1.23 volts, though it does need to be higher than this in practice due to the kinetics. And there's many, many different types of electrolyzers. You can run them in acidic conditions, in alkaline conditions, with solid electrolytes instead of liquid electrolytes. And a lot of research goes into this every year. So how do these work? So first, at the anode, which is here on the right-hand side, your water comes in and basically gives up electrons to the anode and forms oxygen gas. And it releases 4 protons in the process. So you see it's a charge balanced process because you're producing 4 protons or H+ ions and 4 electrons. Those electrons then travel round the external circuit, so up from the anode and over to the cathode. And here at the cathode, H+ ions or protons combine with the electrons, so they're reduced to form hydrogen gas. And these H+ ions are basically shuttled from the anode side to the cathode side by this orange bar in the middle of the diagram is a membrane which sort of separates the anode and cathode and allows the H+ ions to move from side to balance out. So overall, you have 2 water molecules being split into 2 hydrogen molecules and an oxygen in a green way without CO2 emissions in a process that has been tested industrially, so it works and is green. But it currently only makes up a tiny amount of production. And the reason it's such a tiny amount of current production is because hydrogen from natural gas is quite cheap. So it only costs from less than $1 to $5.7 per kilogram. I should note that this is highly dependent on gas prices, which saw a large increase in 2023 due to the energy crisis, which was sparked by the war in Ukraine in 2023. So it's very dependent on geopolitics. So it's not very price stable, but it's still significantly cheaper than electrolysis because that can cost up to $12 per kilogram of hydrogen at the minute. So in terms of economics, it makes no sense to build electrolyzers. It's just too expensive. So that makes our decarbonisation much harder because you'd need either governments to subsidize it a lot or for energy prices to come down significantly. So costs need to be brought down if we do want to replace the fossil fuel production. And another part of why electrolyzers are so expensive is they have very large capital costs. So these catalysts you use in your anode and your cathode are typically rare metals. So things like platinum, iridium, which are very expensive. Also things like nickel, ruthenium, rhodium, lots of very expensive metals. And as I say, energy costs are very high. So you'd need very cheap renewable green energy to make it a truly renewable process. And a lot of research in electrolyzers from a chemistry perspective, because that's my field, is into designing new catalysts that are either cheaper, so they don't use as much of those expensive metals, or they're more efficient, so you get more hydrogen for the cost you're putting in, so you can recoup the capital costs on a shorter timescale. Or looking at basically different types of electrolyzers to try and get cheaper and more efficient. And people are building them. So in 2023, there was 1.4 gigawatts of capacity. In 2024, it was forecast there was 5 gigawatts. But this is still quite small compared to the hydrogen you get from fossil fuels. So the International Global Hydrogen Report, which is a report which looks at all the hydrogen industry, has forecast that there might be 49 megatons produced each year by 2030, which is about half of the current hydrogen production in total. And that's if you add up all the electrolysis projects across the world that have been announced. So even then, you're only 50% to replacing current capacity. I remember, if demand goes up, then you need even more. So there's a very, very long way to go if we want green hydrogen production. And another method of producing green hydrogen, which is not used industrially yet, is photocatalysis. And this is actually what I research as a PhD student. So in photocatalysis, instead of using electricity as our input energy, we use light or sunlight as the energy source to split the water. So as there's no input energy, it doesn't matter about whether we have a renewable energy grid or one that's still got some emissions, because we're not using any electricity. We're just using sunlight, which is obviously a renewable energy source. And to do this, we have a photocatalyst, which is a semiconductor. So it's got two bands, a valence band and a conduction band. But basically, all that happens is that a photon of light comes in and the photocatalyst absorbs it. An electron moves from the valence band to the conduction band and leaves basically what we call a hole. So it's sort of like the absence of an electron in the valence band. So you have an electron and a hole. One is positively charged, one is negatively charged. So that's the first thing. The second thing is these electrons and holes move to the surface of your particle. So if you've got this photocatalyst, if your holes and electrons are generated in the middle, they'll have to move to the surface of the particle so that they can react with the water in the system. And then the third step is the hydrogen and oxygen are generated on the surface. So if we look at the top right, where it says HER, this is where the hydrogen evolution happens. HER means the hydrogen evolution reaction. So here, your electron is at the surface of the catalyst and reacts with a H plus ion, and it generates your hydrogen gas. And you might have a co-catalyst on the surface of the particle, which might be, again, a small bit of platinum to help speed up the reaction. And then on a different part of the particle, your hole will have gone to the surface. So here where it says OER, and your water molecules react with holes to produce oxygen gas and 4 H plus ions. Here, when we were talking about what hydrogen could be used for, here we have the hydrogen buses that are currently in deployment in London, the taxis that were used in the Olympics. In the bottom right, we have the hydrogen planes that are being prototyped. The unfortunate Hindenburg disaster of 1937, when they had a hydrogen blimp, and of course, it's used in space travel. Now, when we talked about how much hydrogen is produced each year, we produce 97 megatons, and you can see on the right-hand side here, with this large amount being in industry, and 60% of that being methanol production, with that going into ammonia. So here, when we talked about the Haber-Bosch process, here's a diagram of the process. So you have nitrogen and hydrogen feed gases going into a reactor. These are compressed and heated, are reacted, and then they get condensed. The ammonia is siphoned off here at the bottom, and the gases are then recycled back, and you can produce ammonia. And then ammonia is made to use fertilizer. The hydrogen is produced mainly from fossil fuels, with these reactions in the top right. So you see here that you can steam reform methane to generate 3 molecules of hydrogen, and then you can use a water gas shift to get another one, but you're producing a molecule of CO2 at the same time. So it's a directly CO2 emitting process. And you can see here on the right, almost all of the hydrogen production is from fossil fuels, and the rest of it is from byproducts and from other industry uses. So our electrolysis was a green way of producing it. So over here on the right, you have a diagram where your water comes in at the anode, gives up protons, electrons, and produces oxygen gas. Your electrons go around the circuit, and on the other side of the cathode, your hydrogen, your H+ ions combine with electrons to produce hydrogen gas. And you have this orange bar, which is a permeable membrane for which the H+ ions can go across, and you split the water overall. So then this side just had the challenges which I read out to you, listed down. So electrolysis is more expensive. We need to bring down the costs. And there's forecast projects, but there's not that many. So here's where we got to with the photocatalysis. So we have this diagram on the right-hand side. So this is our semiconductor photocatalyst. We have a photon of light coming in and generating an electron and a hole. These then migrate to the surface. So your electron goes over here and your hole goes over here. And then these react, the electrons react with H+ ions to give you hydrogen gas. Your holes react with water to give you oxygen gas and 4 H+ ions. And you often have co-catalysts on the surface to make these reactions go quicker, more efficiently. With HER, you'll have something like platinum, and OER will have something like cobalt oxide. And you can combine this with electrocatalysis, so electrolysis. So if you attach your photocatalyst to an electrode, you can then have a circuit where you're putting in electricity, and then if you shine light on it as well, you've then got 2 input energy sources, and sometimes that can give you higher efficiency, so you can split more water for the number of joules of energy you're putting in, which is one way of using this technology. But the problem with this is, in contrast to electrolysis, where you have very high efficiency in electrolysis nowadays, but it's just too expensive. Photocatalysis is still expensive, but because it's got very low efficiency, so it just doesn't produce anywhere near as much hydrogen as electrolysis does. So the challenge in photocatalysis is not to make cheaper, more efficient electrodes, it's to make just more efficient photocatalysts, which can get even a couple of % more towards electrolysis. So for context, electrolysis is about 90% efficient nowadays, sometimes higher. Photocatalysis, maximum 10 or 11% efficient at converting energy into hydrogen. So there's a big task there if this is ever going to become a viable industry and help us to decarbonize hydrogen production. And so my sort of last slide is about something you will hear hydrogen talked about, which is a hydrogen economy. So this is nothing to do with making fertilizer, making chemicals, or any of those uses which we have currently, but it's about a future system where hydrogen is used as a way of storing energy. So it's sort of related to the idea of hydrogen as a fuel, or using hydrogen as a heating product. So you'd make this hydrogen in a way, hopefully a green way, as we've discussed, and then either it would be burnt in a house to release the energy as heat, or it would be burnt in a plane, or in a fuel cell in a plane, or a car or a bus, as a means of storing and transporting electricity. And the reason it's floated is because chemical energy storage is going to be necessary when we produce a lot of electricity from renewable energy. So if you think of your wind power, your highest power is when it's windy, but when it's not windy, your output drops significantly. And with solar power, you get power in the day, but not at the night. So you need to be able to store this energy um, so that you can store it at peak production times and then release it at peak demand times. So you can use batteries, and there's a lot of work going to make large-scale battery storage systems. But there are limits on batteries. Batteries are not good for storing energy over long time periods because it can be bad for battery stability. So instead, it's proposed that you could use hydrogen. So if you take your excess electricity and put it into an electrolyzer, which is sort of the process in this flow chart over here, you can convert your electricity into hydrogen gas. And then whenever you need that electricity, you can then put it into a fuel cell, which is something that takes hydrogen and mixes it with oxygen and then generates electricity and water. So it's sort of the reverse process of an electrolyzer. And basically using these two systems, you can convert between electricity and hydrogen gas to basically store and release energy when you need it, which is a great idea. But there are a few problems with it in that hydrogen gas is really hard to store. And this is to do with back at the start of the talk when I said hydrogen is the smallest diatomic molecule. It's really small and it's really low density. So it takes up a very large volume. So you need to condense it a lot. You can't store it as a liquid because it condenses at 20 Kelvin or minus 253 degrees C. So the only thing you can cool hydrogen to a liquid with is liquid helium. And helium is very expensive because it's not naturally abundant on Earth. The only sources on Earth are from radioactive uranium, so it's very hard to come by. And not only can you not store it as a liquid, really, it's very, very flammable. And if you have a flammable gas at high pressure, if something goes wrong, that's very explosive. So a lot of research is going into sort of coupled processes wherein you make your hydrogen from electricity, but then you take that hydrogen and make ammonia. So you could do it in the Haber-Bosch process, or there are people working on other electrochemical ways of converting hydrogen to ammonia. But the benefit of doing so is ammonia you can store as a liquid, and you only need 6 bars of pressure to do so. So it's not that bad. You don't need liquid helium or anything. You don't need to cool it down. You just need to pressurize it. And once you've got liquid ammonia, you can then put it on the back of a truck and transport it. So then your electricity is not only stored, but it's mobile. So you can move it to where you need to use the electricity. And then similar to how we use a fuel cell to convert hydrogen gas to electricity, you can use different types of catalysts and reactions to convert ammonia back to hydrogen gas, for instance, in a fuel cell. And then that hydrogen gas goes in a fuel cell and makes electricity. So you can sort of make these coupled energy storage systems, which may make it easier for the national grid, for instance, to decarbonize and allow greater renewable production without the need for like a base load of generation. Because currently we have large numbers of gas power plants, which have to be turned on when we have low renewable output. So the idea with this is if you can store excess electricity and instead release that when renewable output is low, then you can reduce the need for those last gas power plants, and that's how you may be able to decarbonize the rest of the grid. But of course, everything has problems. So this sort of system requires electrolyzers. And we want electrolyzers to decarbonize hydrogen production so that we can get net zero fertilizer, steel, chemicals industry. So if we're then using electrolyzers as an energy storage medium, then we're going to need even more electrolyzers than we needed before. So there's no easy answer to any of this, apart from a lot of work needs to be done. A lot of infrastructure needs to be done. And hydrogen is inevitably going to play a part in that. And decarbonizing its production is going to be central to decarbonizing global CO2 emissions, because of course it's such a large proportion of them. And if we can crack that, it may even help us do that last bit of decarbonization on the electricity grid as well. So yeah, I have a few links to resources which I used when I was preparing this. So here's some information about some of those uses I mentioned earlier. So Toyota's hydrogen car, Airbus's planes, and the London hydrogen buses. If you want to read about Hindenburg disaster, there's a link you can follow there. The rocket fuel stuff as well. If you're interested in hydrogen, its production, use, global energy projects, then the Global Hydrogen Review is published every year with all this information in. And there's a similar report about the use of ammonia technology. And the third link is about synthetic fertilizer. And if you want to see how many CO2 emissions you have per hydrogen production method, there's a link there, and a link explaining electrolysis in a bit more detail. So yeah, that's all I've got to say. So I will throw it open to questions.